a more interesting problem actually, how to get the x component of the electric field at point P due to this charge distribution. If you haven't watched the first video, go back and watch it, where we got the y component of the electric field. Now we want to get the x component of the electric field. So if you try to just think about it intuitively, try to sketch what does the potential look like as you move along this line. This line is a line parallel to the x-axis, and it has a y-coordinate, the same value as point P. What would the potential look like? Well, if you go to, I'm going to plot the sketch over here of the potential along this line. If you go to the point P itself, the potential is 0, because you get kq over R1 minus kq over R2, and R2 is the same as R1, and you get 0. The distance is the same, you get exactly 0. So the potential at point x equal to 0, at this point P, it's 0. So this is one point in the sketch. What if you move a little bit to the right? When you move a little bit to the right, R2 is smaller than R1. So what does that mean? It means that when you get the potential due to the positive charge, it'll give you a lower number, because the potential is kq over r. Since R1 is bigger, then 1 over r is smaller. So you have a positive number that's small, and you have a negative number that's large. So that when you add those two numbers, you get a negative number. So the potential becomes negative when you go to the right. I'll illustrate that by putting a point here that is negative. What about when you go to the left? Well, the potential is the potential due to this charge plus this charge. Now, when you go to the left, R1 is smaller than R2. So the potential due to the negative charge is a less value than in magnitude wise than it is for the positive charge. So you get a positive number that's large, and you get a negative number that's smaller because the distance is bigger. So the potential will be positive. I'll put here a value that's positive, some positive value. I don't know what the value is, but I know it's positive. When you go to infinity, what does the potential become? Either positive infinity or this side or this side. When you go to infinity, the potential becomes 0, because the potential goes like kq over distance, and when r is infinity, you get 0. So that means that the potential here, it goes negative and then it becomes 0 in the end. And here it's positive and then it becomes 0 in the end. Connect the points. This is what the sketch of the potential would look like. And you can tell then straight away from this sketch that the electric field, the x component of the electric field, will be positive. How can you get that? Because Ex is minus partial v by partial x. So what is partial v by partial x? It's the slope of the potential at this point. Now, is the slope here at this point positive or negative? It's negative. So you have a negative value multiplied by minus 1, you get a positive value. So that means Ex is going to be positive, which is exactly what we expect. This just gives you the sign, but it doesn't give you the value. How would you get the electric field, the x component of the electric field at point P? Exactly. Well, this is a sketch of the potential, again, just to illustrate the idea that here, as you go, the positive values are the red values, the negative values are the blue values. As you go from infinity to here, the value gets more and more positive, more and more red, and then it gets white again, so it gets to 0. Then it gets negative, means blue, more blue, and then it gets less blue, and it gets to 0. This is just a plot, a nice graphical plot of the potential. So how would we proceed? How would we get the electric field, the x component of the electric field at point P? Well, if you know the potential at point P, it's not enough to get Ex. We know the potential actually at point P is 0. So how would you use that to get the electric field, the x component of the electric field? You can't. So what do you need to know in order to get Ex? Remember, to get the electric field at a point, you need to know how the potential changes as you move in the x direction at that point. So you don't just want the electric field at point, the potential at point P, You need to know the potential as you move along this line. So how about getting the potential at an arbitrary point on this line called P prime, which has coordinates x and y? What would the potential at this point P prime be? The potential is just kq over r1 plus k minus q over r2. It's a very simple value, simple result. Now, since point P prime has x coordinate x and y coordinate y, can we write down r1 and r2 in terms of x and y? Yes, because if you look at this triangle, r2 squared is y squared plus this distance squared. But what is this distance? It's x minus a. So r2 is just the square root of y squared plus x minus a squared. And what is r1? If you look at this big triangle, r1 squared is equal to y squared plus this distance squared. What is this distance? It's just x plus a whole squared. So that means that r1 is the square root of y squared plus x plus a whole squared. That's the math. You just put r1 to be this value, r2 to be this value. That gives me the potential at point P prime along that line that we wanted. So now, how would you proceed? You know now how the potential depends as you go in the x direction. Remember, along that line, y is a constant. Y is not changing. That line was a horizontal line, and y is the same value for every point on that line. So the only variable here is x. So how would you get the electric field, the x component of the electric field at point P? What are the steps? If you get the x component of electric field at this arbitrary point, which is minus partial v by partial x, and then you can get the electric field at point P after that. So first get the electric field, the x component of electric field at point P prime, and then get it at point P. So this is the way you can solve this. So the electric field at any arbitrary value of x along that line is minus partial v by partial x. So you need to just take the derivative of this with respect to x and multiply by -1. This will give you the x component of the electric field at any point along that line. Now, if you want to get the Ex at point P specifically, you just substitute for x equal to 0, and you'll get the Ex for that particular point P. So the steps are as follows. You first get minus partial v by partial x, which is this. You can do the math yourself. It's very easy to take the derivative of this with respect to x. It's a partial derivative. And then if you want to get the electric field at point P specifically, which is characterized by having x equal to 0, you just put x equal to 0 here. When you put x equal to 0 here and here and here and here, you get a over this, and then you have a minus, and then you have minus a over this. So you can see here that the minus and minus will give you a plus, and this term is identical to this term, so you just get twice of this term. So the electric field turns out to be 2keqa over y squared plus a squared to the power 3 over 2. And if you go back to the problem that we solved before, when we solved it using Coulomb's law, this is exactly the value of the electric field that we got before. So this illustrates how we can use the concept of potential to get the electric field rather than starting with Coulomb's law directly. And this shows you that the concept of potential is a completely equivalent way of characterizing the effect of charges around in the region or space around them. One way to characterize the effect of charges is to calculate the electric field at every point in space. That's the way we did it before. And another way is just to get a scalar field called the potential. It's just a number at every point in space. There's no vectors at all. And then once you know the potential at every point in space, you can get the electric field by simple differentiation. So these two ways are equivalent. This is superimposing both on top of each other, just to give an idea of how it looks.